Hello students, it is lecture 2 of mathematical physics. So in the previous lecture, the last lecture, we completed the bisection method and Newton-Raphson method. These two methods are the methods used for finding the roots of an equation or solution of an equation. Okay, the main formula used in bisection method was x2 is equal to x0 plus x1 by 2. In general case, like xn plus 1 is equal to xn minus 1 plus xn divided by 2. In Newton-Raphson method, xn plus 1 is equal to xn minus fxn divided by f dash xn. Okay, please check out the previous video for more information regarding these two methods. We will be studying the regular Fourier method and secant method later on. So right now we're going to discuss the error or convergence. Okay, the point of error or convergence come into the communication when we need to decide which method is actually required for solving any question. Okay, so the discussion of error or convergence. Here we have solved one example which we solved earlier using the bisection method. The solution of e raised to power x minus x is equal to 0 using Newton-Raphson method. Okay, on solving this particular question, we see after the, it's the first iteration, second iteration and third iteration. After the third iteration, we got the result 0.567. Okay, but if we check out the last solution of bisection method, okay, here we solve the question e raised to power x minus x is equal to 0, and it took about 4 iterations to get to an answer that was 0.5625, which is far away from the actual answer. But in Newton-Raphson, what the answer we got after the third iteration or the third solution is 0.567, which is the closest to the actual answer. So from this calculation we can get the point that the convergence of Newton-Raphson is faster or larger as compared to the bisection method, or the Newton-Raphson method will always be preferred over the bisection method. So we move forward. Here we will do a detailed analysis of the error or convergence. Okay, the first topic which we have taken for convergence thing is bisection method. Under bisection method, the general formula is xn plus 1 is equal to xn plus xn minus 1 divided by 2, where let xr be the root. Okay, what we are considering, the root of the equation is xr. Okay, so if we subtract xr in both these equations, what we may write, like it will not change the equation because we are reducing xr on both of the sides. So xn plus 1 minus xr is equal to xn minus xr plus xn minus 1 minus xr by 2. These two are same things because we have just subtracted xr on both of the sides. It does not alter the equation. Now xn plus 1 is basically our calculated result. Okay, and xr is the real result, that is the root. So their difference gives the error, right? Similarly, xn minus xr, xn minus 1 minus xr. So it is the error for nth observation and it is the error for n minus 1th observation. Correct? So what we can write is xn plus 1, en plus 1 is equal to en plus en minus 1 upon 2. That is the error. What is exactly an error? Error is the real value minus estimated value, or estimated value minus the real value. Okay, so it was the estimated value, it was the real value, and we subtracted, we got error en plus 1 is equal to en plus en minus 1 divided by 2. So En plus 1 is equal to En plus En minus 1 divided by 2. Now, as En and En minus 1 are basically of same order and there is not much difference into them, okay, like these are error to a pretty finite range, like quite small. So instead of writing both of them, we just kind of neglect this part and we may write En plus 1 is nearly equal to En by 2. See, we are not just ignoring the fact, we are not writing it as equal to, we are writing it as nearby. Okay, nearby approaches means like it is not exactly the same thing but close to that. Okay, so as I have mentioned here, En and En minus 1 are nearly of same order. Okay, so hence we have just neglected one. So this particular thing shows that for every n plus 1 the error reduces by half. Okay, for example, whatsoever the error is now, it will get reduced in the next. For example, the error for this observation is 5. In the next observation, the error will be 5 by 2. In the next observation, it will be 5 by 2 by 2, that is 5 by 4. In the next observation, it will be 5 by 8. Okay. So this shows that the error of the next step is dependent linearly on the error of the previous step. Like En plus 1 is dependent linearly because the power is 1 only, right? It is linearly dependent on En, that is the error of the previous step. So whenever we write the general formula for it, we can write it as En is equal to mod x1 minus x0 by 2 raised to power n. Like how this 2 raised to power n came? Here we can see an example. It is a line. This point is x0. Sorry, this point is x0. It is x1. So when we are asked to find the middle point, the midpoint will be x1 minus x0 by 2, correct? Now when we need to find the middle point of these two, it will be like, suppose this is so whatever the middle point it is here, this distance is x1 minus x0 by 2. Okay, and if we need to find out its middle point, we will go by x1 minus x0 by 4. By 4 came here just by dividing by 2, like, okay. So as in every step we are moving, we are dividing the error by 2. Okay, and if there are n steps we are taking, we will divide the value x1 minus x0 by 2 raised to power n times. Okay, so that's why we have written En is equal to x1 minus x0 divided by 2 raised to power n. Important thing mentioned here is this error is linearly dependent, like this error is linearly dependent on the error of previous step, and it is called linear convergence. Okay, now when we talk about Newton-Raphson method, under Newton-Raphson method we consider a function whose fx is equal to 0, let the function fx is equal to 0. When we expand this function using Taylor series, we write it as fx is equal to fxn plus x minus xn f dash xn plus x minus xn raised to power 2 f double dash xn, like f double prime or double dash xn divided by 2 factorial, and later on we kind of do not consider the later on part because the value is quite low. Okay, we take these first 3. Okay, put x is equal to xr, like that is the root. So at the condition of the root, like if a number is a root of a function, its value is equivalent to 0, right? So what we get here is 0 is equal to fn plus, in place of x we are replacing it as xr minus xn f dash xrn f dash xn plus f xr minus xn whole square f double dash xn upon 2 factorial, and we mark it as equation 1. Now when we use the formula of Newton-Raphson method, what is the formula? Xn plus 1 is equal to xn minus fx divided by, or fxn divided by f dash xn, right? So from this formula we can find out fxn is equal to xn minus x plus 1, like we move this thing to this side and this thing to this side, xn minus xn plus 1 into f dash xn, and we put the value of fxn into the above equation and we just solve the equation. Here the solution is given, you can check out. So on solving it, we reach a point where we get xr minus xn plus 1, xr minus xn. From recent example, like earlier we saw it, real value minus estimated value gives out the error. So xr minus xn plus 1 is the error for n plus 1, xr minus xn is the error for like the nth observation. So 0 is equal to en plus 1 f dash xn plus en square upon 2 factorial f double dash xn. Okay, on further like shifting terms from left to right, what we get here is en plus 1 gives out minus en square f double dash xn divided by 2 f dash xn. Okay, the prime observation from it is that en plus 1 is directly proportional to en square. It means it is quadratic convergence. For example, if the error in this step is like 0.2, the error in next step will be 0.04. The error in next step will be 0.0016. Okay, what in bisection method we get is the error is linearly dependent. Okay, linear convergence. But when we come to Newton-Raphson method, the error is like quadratic convergence. Okay, it approaches towards the correct result faster as compared to bisection method. Under bisection method we need many attempts to reach to the final result, while in Newton-Raphson we can approach the result a little faster. Okay, and here is a table I have kind of made. Newton-Raphson has an order of convergence. Order of convergence is basically the power of dependence. Like here the power is 2, in the bisection method the power was 1. Bisection method is also 1 power. Regular falsi will be 1, and secant method will have 1.618 or 1 plus under root 5 divided by 2. Therefore, Newton-Raphson is better than bisection method. So the next topic which we'll study is numerical integration. Numerical integration is basically generally for computer programming and all. It helps for computer programming purpose, and it is also used to approximately find the values of definite integral. And whenever we discuss about definite integrals, it is the numerical integration theorems are, or numerical integration methods are one of those which can be used to find the definite integrals. Okay, see, the methods under the numerical integration which we will study today is the trapezoidal method. It's the first one. See, what is a trapezium? You must have heard of trapezium. Trapezium is basically a 2D figure having like a pair of parallel sides, and yeah, like you draw a trapezium, like draw any parallel side and just join the other lines. It's a trapezium, and the area of trapezium is 1 upon 2 into sum of parallel sides into the height or the distance between those parallel sides. See, as you all know, integration is basically the area under the curve. Like whenever we discuss about integration, what do we calculate is basically whatever the area it occupies in the curve. Okay, the approach behind the trapezoidal method is we breaks down the curve into small trapeziums, and we add out their areas and we get the total result. Okay, so I is equal to a is to b, like that is the limit from a to b, fx dx. we draw this function. It is a function. A is the initial limit, B is the final limit. A we call as x0, B is called as xn, and there are minute distances at which we make other points like x1, x2 and xn minus 1. Okay, so what is I? I is basically the area which is equal to the sum of area of trapezium. What is we need to know this thing. The h is the step size. Step size is basically this distance. See, this distance is fixed under this method. Okay, we need to take the intervals of regular size. Okay, so what is the area of trapezium? We apply here 1 upon 2 into f0 plus f1. What is f0? F0 is this side and f1 is this side. That is, these are the parallel sides. The sum of parallel sides into h. H is the height. And similarly 1 upon 2 f1 plus f2 into h, and it continues. On adding it all, what do we get here is I is equal to h by 2 f0 plus fn, the first term and the last term. And since other two terms, like all the terms in between, are repeated twice, or like are repeated, so we write 2 into f1 plus f2 plus f3 dash 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 fn minus 1 up to the second last term. Now, as we know, f0 is fx0, like f1 is f0 fx0 plus h, f2 is fx0 plus 2h. Like, we are moving in the intervals of h, right? If it is, the distance here is x0 plus h, x0 plus 2h, x0 plus 3h, x0 plus 4h, and that is the thing mentioned here. Fn is equal to fx0 plus nh plus is equal to fxn. So the relation that is important here is n is equal to xn minus x0 upon step size. Okay, or step size is equal to the final minus initial upon the number of iteration, or number of divisions we need. If we want to approximately calculate an integration, then we decide the h. See, if h is very small, you get more accurate answer. For example, if there are very tiny intervals causing a trapezium, the area that will be calculated will be more accurate as compared to making just two trapeziums over here. Because if you make just two trapezium over here, the area will be the remaining area will be left out. Okay, so for better precision, we take the value of h pretty small. Now, here's a question that came into the exam of TIFR. Evaluate this definite integral. See, there are situations when it's not easy to calculate definite integral using the analytical method. Okay, so what we can do is go for these methods like trapezoidal method, which will help us to calculate it quite easy, as TIFR allows calculators, and it will be easy for you to calculate the answer easily. Okay, so let us integrate using trapezoidal method. Step size, the step size which we are using here is 0.125. Okay, see, as the interval, we can see the interval is 0.75 minus 0.5. The difference is 0.25. We need to at least take two step size. Okay, for that, like, we need to take at least two blocks or 2n in between. For that, we take the step size as 0.125. Okay, you can take any other smaller step size too, but it's easier to go for this one. Okay, I is equal to h by 2 f0 plus fn plus 2 f1. See, as we went for 0.125, it makes the division 2. Okay, n is equal to 2, right? So whenever we do the formulation thing, we write f0 plus fn is equal to 2f1, where 2f1 is the middle term. Okay, 0.125 e raised to power, we put the value of this function, and using the calculator we calculate it as 0.00232. Looking at the options, the closest option is 0.00215, hence it is the correct option. Another example, it was the example of the trapezoidal method. Another method for integration is Simpson 1/3 rule. Okay, under Simpson 1/3 rule, this formula is given to us, and a mandatory condition is also given with respect to the formula. The formula is I is equal to h by 3 f0 plus fn plus 4 f1 f3 f5 data dash plus 2 f2 f4 f6. See, the formula looks formula looks complicated. Okay, but in simple terms we can say h by 3, first term and the last term, like f0 and fn, plus 4 into sum of odds plus 2 into sum of even. Okay, these are 1, 3, 5 odd functions, and 2, 4, 6, these are even one. H is the step size. Similarly, in like the previous step, n is equal to xn minus x0 upon h. Okay, and it is similar to the previous thing, like x0 is fx0, xn fxn, f1 is x0 plus h, f2 is f into x0, f x0 plus 2h. It is same to the previous step. Okay, so let us solve one question using this Simpson 1/3 rule. Here is a simple question: integrate 0 is to 1 x square dx using Simpson 1/3 rule, and step size given here is 0.25. See, earlier the step size I mentioned was 0.125, but it leads to 8 calculation, like 8 times doing the thing, or a larger calculation. So instead of going for a larger calculation, we restricted it to a pretty smaller version, and we took n is equal to 4. Okay, on putting out the values, we get I is equal to h by 3 f0 plus fn plus 4 into function at odd points plus 2 into function at even points. H by 3 f0 plus f4, like the first term is f0, final is f4, plus 4 f1 plus f3 plus 2 f2, correct? So I is equal to 0.25 by 3, and then 0 square plus 1 square plus 4 into 0.25 square plus 0.75 square, like this f1 is 0.25, f3 is 0.75, okay, and f2 is 0.5. On solving out this calculation, we get 1 by 3 as answer. The thing about this method is, here we got 1 by 3 as the answer, and it is accurately correct, but we need to know these are approximate methods. It will be a coincidence if it is giving the exact answer. Okay, there is some deviation, like there is some difference between the exact answer and the calculated answer, but it is just a coincidence this time. There might be other question in which you won't be getting the exact answer using this method. Okay, like in the previous MCQ of previous question of TIFR, here we saw the answer was 0.00215, but using this method we received 0.00232, hence it was the closest, we chose this answer. Okay, see, these two methods are important. Like integration question have been pretty common in competitive exams for GATE, NET and etc., like TIFR etc. So kindly practice these, and thank you.